Okay, last question, question 10. So we've got a model dynamo. There's the dynamo. This is connected to a voltmeter. So let's connect that up to a voltmeter and a screen. Clearly they can turn the handle that way, or they can turn the handle the other way. And it produces a DC output because it's a dynamo. Okay, so it says they rotate the handle to make the coil spin inside the magnet. Makes loads of sense. For A, we can see that it's negative value there. What's that? 0.75. So minus 0.75. Then they rotate the handle differently, and we've got a new reading of 1.1. I get that ish. 1.1 volts positive. So clearly they've rotated the handle, say, that way on that one, and that one on that one. That's why we've got a different polarity. And they must have rotated this one faster because it's produced a high voltage. You know, if you do it faster, you end up with, so let's imagine, here's a slow one. We end up with a low voltage and a low frequency. And if I spin it super fast, I end up with a high frequency, but not just a high frequency, I also increase the voltage. Okay, so which row shows how the rotation of the handle has changed? So B's got to be faster than A faster than B, A faster than B, A slower than B. So it's got to be a choice of those. A is definitely slower than B. And this one is positive, so it's got to be opposite, so it's going to be C. The teacher connects the dynamo to the lamp. It is now more difficult for the teacher to rotate the handle. Okay, well, in there we've got some added resistance. I'm always going to answer it in terms of, if I spin a dynamo, when I make a current, okay, that is going to be opposite. So you can imagine I'm making a current. This now creates the motor effect that counteracts what I'm doing. All right, so you imagine I'm spinning it down, and then I make a current that produces a force that goes against me. So there's force me, and here's force of the motor effect. So why is it more difficult? We can talk about it in terms of resistance. I'm just going to do the current produced induces a magnetic field, which produces a counteracting motor effect. Next part, here is a transformer. Number of turns on the primary coil. So instantly I know that's the voltage in. I can see that this is a step down transformer. Calculate the potential difference. So you've got your ways of doing it where you just find out your ratio, and we know that I want the voltage to go down and the current to go up. Or you can use the equation that they give you, which is this. So you can see that I've just rearranged it. So NP over NS equals VP over VS. It says calculate the potential difference across the secondary coil. So that's this. And we've done this loads of times now. So I end up with the voltage on the secondary is NS times VP. So if I just explain that, we've got NP over NS equals VP over VS. Well, my first job is divide both sides by VP. So I end up with NP over NS multiplied by VP, oh God, equals 1 over VS. And the best way to get rid of this reciprocal is flip that over. And you can see that there. That NP's gone, NS VP has gone to the top there. And then NP's underneath. I think that makes sense. You can see that there. That should say NS, apologies. Okay, but at least that now makes some sense. But we've done this quite a few times. Plug that all in and we get 5.2 volts. Next one, we've got a device can be used as a loudspeaker or as a microphone. So in a loudspeaker is we're going to put in a current to get a vibration out. Okay, so this is going to be the motor effect. In the other, we put in a vibration, and that produces me a current. This is the generator effect. So we've got to compare them. So that's how are they the same? How are they different? Well, both of them are using induction. So that's something I can add in there. And then we're just going to go through. So a loudspeaker uses the motor effect to produce a vibration, to move air. The microphone uses the generator effect, where a vibration vibrates a magnet. Okay, so a vibration of air vibrates a magnet. So here we go. The loudspeaker has an alternating current input This induces a changing magnetic field in the coil, and you'll see that we've practiced this loads. This interacts with the surrounding uniform magnetic field, and this would be on an annular magnet, so a single pole of an annular magnet. This produces a force which causes a vibration, and that matches the frequency of the AC input. So if I just go through, we've learned for a loudspeaker, alternating current in, this induces a change in magnetic field. This interacts with a uniform magnetic field from the annular magnet, or from the single pole of an annular magnet span. This produces a force, and that force makes a vibration, and the frequency of the vibration equals the frequency of the alternating current. So that's it's kind of spammed out in the memory method way. Now I'm going to do the opposite for the other one. And this one we can see, for me to do as a microphone, it's going to be the vibration. It's going to make this vibrate, and then that's going to move this inside the coil, or move that coil because it's attached to the cone. That's going to move that in and out, and then we're going to get an alternating current that matches the vibration that we put in. So go to the next one. The microphone uses air's vibration to move the cone. This vibrates the coil around the single pole of the annular magnet. The coil now experiences a change in magnetic field, and this induces a voltage or a current. The output alternating current will match the frequency and the amplitude of the sound wave. And there you go. And practice that one quite a bit, because it's tricky at the start, but actually it's a nice easy 6 marker. Right.